Hello everyone and welcome to Robot Operating System version 2 Jazzy Jalisco tutorials. In this tutorial, we explain how to model and simulate a mobile robot in the Gazebo simulation environment, and we explain how to add a Lidar sensor to this simulation. The simulation is shown over here. Here's our mobile robot. Obviously, it's a differential drive robot. And on the top of the robot, you can see a Lidar sensor represented by this black cylinder. The Lidar sensor provides a 360 degrees scan of the environment surrounding the robot. Namely, if I click over here, you can see all the rays. And if I deselect this button, then you can see only the reflected rays. That is, Lidar can provide us distance measurement between the robot and its obstacles. For example, it provides us a distance measure between the robot and this cylinder over here, or this box, or this sphere over here. And if I click over here, and if I press Ctrl C, you can see the measurements. Here they are. This is the array of measurements provided by the Lidar. Infinite values represents to rays that are not being reflected. That is, to the rays, for example, these rays over here. On the other hand, the non-infinite values, for example, this value over here, represents the distance between the Lidar, or better to say the robot, and the obstacle. By using this terminal over here and the keyboard keys, we can control the robot motion. Namely, by pressing certain keys, I can steer the robot left or right, or I can even pass these obstacles. For example, I can do something like this. Let me just increase the velocity so you can see it better. I can, for example, pass these obstacles like this straight. It's worth mentioning that the Lidar has a finite measurement range. Namely, it can only measure 12 meters. You can adjust this later on in the simulation. So currently, you can see that the Lidar is not measuring anything. This is because we have passed the boundary of 12 meters. On the other hand, if I return back, and let me increase the velocity over here so you can quickly return, you'll see how the Lidar measurements will reappear once we reach 12 meters, and you can see them over here. And this is really nice. In this video tutorial, we explain how to write a URDF and Zacro file that implement the robot model and the Lidar model. Then we explain how to write these bridge parameters files that bridges ROS2 and Gazebo topics such that you can establish a link between ROS2 and Gazebo, and we will explain how to write a complete ROS2 package from scratch. In addition to this, we have created two manuals explaining all the steps that you need to perform in this video tutorial. We will closely follow this manual. Here is the first manual. It is 10 pages long, and it explains all the commands that you need to type. This manual is specially designed for people who are completely new to ROS2 and Gazebo. In addition to this manual, we have created an additional manual explaining graphical description, dimensions, frames, and formulas for implementing differential drive robot. Here it is. It is 7-page long. Links to all the files presented in this video tutorial, as well as to these manuals, will be given in the description below this video, as well as in the comment section below. Before we start with explanations, here's the license and the copyright notice. This document, develop code files, lesson video, and all the provided material are referred to as the learning material in the sequel. The learning material is the ownership and the original work of Dr. Alexander Haber, who is the author of this tutorial. Then, you have the right to use the learning material for personal educational use and strictly for non-commercial use. Then, the learning material should not be copied, redistributed, or publicly posted on public or private websites, code repositories, and social media platforms. The learning material should not be reproduced manually or automatically using an algorithm or an AI model from this video and then posted on public or private online repositories. Unless allowed by the author, the learning material should not be used as lecture material on online learning platforms and in university courses. Unless allowed by the author, the learning material should not be used to organize courses for training engineers working in companies or paid academic researchers, such as paid students, paid postdocs, paid professors, etc. The provided code files and learning materials should not be used to train an AI algorithm or a large language model, and then, unless allowed by the author, the learning material should not be used to produce academic papers, student reports, or other documents. Okay, let's start with explanations. First of all, this video tutorial is developed under the assumption that an average viewer knows very little about robotics and robot operating system, and consequently, we will spend a significant amount of time explaining all the commands. First of all, let's start with the prerequisites. To implement the material presented in this tutorial, you need to have Linux Ubuntu 24.04. Do not use Windows Subsystem for Linux or WSL since you might have issues displaying graphics. Install Linux Ubuntu on a computer. If you have a Windows computer, then you can install Linux Ubuntu in parallel to the Windows operating system by using a dual boot approach. To verify that you have the correct Linux Ubuntu version, let's open a terminal. Click here and search for terminal. And then over here in the terminal, type this lsb_release-a and let's see what is the output. You should see Ubuntu 24.04 or something similar. Namely, this third number really doesn't matter. The first two numbers are very important. Then you need to have ROS2 Jazzy Jalisco installed on your system. First of all, I created a separate video tutorial explaining how to install ROS2 Jazzy Jalisco. You can find that YouTube tutorial on my YouTube channel. Simply go to the channel and search for install ROS2 Jazzy on Linux Ubuntu. Let's verify that ROS2 Jazzy is properly installed. To do that, we will list the content of this standard folder that contains the ROS2 Jazzy installation. And if this folder is non-empty, this means that most likely ROS2 Jazzy is properly installed. However, to completely verify that ROS2 is installed, let us first execute this setup.bash file, and then let's print the ROS distribution environment variable, and if you see Jazzy, this means that ROS2 Jazzy is completely installed on your system and you can proceed further. The next step is to install the necessary packages. Now, since a lot of you are completely new to ROS2, you have to remember the following. Every time you want to create a ROS2 package, you need to source the environment. I actually did it by executing this command. However, to show you this once again, close this terminal, then open a new terminal, and in this new terminal, let's type this. Again, sourcing the environment means that you are actually executing setup.bash file. Setup.bash file contains scripts that properly configure ROS2 on your system and that set the environment variable such that you can build the packages. So let's run this and let's continue. Now, before you install any package or anything on your Linux Ubuntu system, you have to make sure that your system is up to date. That is, you need to run these two commands, update and upgrade. And let's run this and enter your password and be patient. Depending on how often you run this command, the execution of this command might take 30 seconds or maybe even 30 minutes. My advice to everyone is to try to update and upgrade everything at least once a day. Then at certain point you will be asked this, press Y and then be patient until everything is downloaded and properly installed. Again, it is very important to update and upgrade everything on your system. So let's be patient and let's wait until this command completes. After everything is updated and upgraded, let's install Gazebo. To install Gazebo, we need to execute this command. Note that in the case of ROS2 Jazzy Jalisco, the recommended version of Gazebo is Gazebo Harmonic, and we have actually installed that version by simply using this command. Namely, this command will automatically detect your ROS2 version and it will install the correct Gazebo Harmonic version. Note over here that Gazebo is already installed on my system. However, in your case, this command might even take several minutes to execute. Okay, now here comes one very important point. If you want to use Gazebo, you need to source the environment once again. Consequently, you need to type this in order to refresh all the environment variables. So let's make sure that Gazebo is installed. First of all, let's type this. This command will return the path of the folder containing the executable called Jazzy, which is the executable for Gazebo. And if you see something like this, then most likely Gazebo is properly installed. However, to verify the Gazebo installation, simply type Jazzy sim and let's see what will happen. This window should open. So let's pick one of the simulation examples, click here and let's see what will happen. Then click here on the play button and then you can move this robot by moving these sliders over here. Good. Let's close this and let's continue further. The next step is to install the necessary packages. Namely, to simulate this robot in Gazebo environment, we need several packages. Most likely you have these packages on your system if you install the complete ROS2 Jazzy desktop version. However, it's still a good idea to try to install everything. So let's start with installation. First of all, let's install Joint State Publisher. Then let's install Joint State Publisher graphics user interface. Let's install ROS Jazzy Teleop Twist keyboard. This package will be used to control the robot. Then let's install the Zacro package, which is necessary for parameterizing the model. And then let's finally install the additional ROS Gazebo tools by running this command. Good. Let's verify that the packages are installed. To verify package installation, you simply need to type package, or actually ROS2 package list, and then you should see the list of all the packages. However, the list is very long and a nice idea is to try to filter the results by using pipes. For example, over here, we are going to list all the packages that contain the word Jazzy in their name. And if you type something like this, you will see all the packages. Good. The next step is to create a Workspace folder and to create the package. For that purpose, let's again open a new terminal. So let's close this terminal and let's search for a new terminal over here. Here it is. And then in this terminal, we again need to source the environment. Don't forget to do this. And then let's make sure that we are in the home folder, and in the home folder, we are going to create a Workspace folder called ws_mobile, and inside of that folder, we are going to create the source folder. So let's now navigate to the source folder. And here comes one very important thing to keep in mind. Whenever you want to create a package in ROS2, you have to navigate to the source folder, and inside of that folder you need to create an empty package structure. That is, you need to create a package template and all the files. To do that, you need to run this command. The name of the command is ROS2 package create. Then you need to specify build type. In our case, the build type will be Amen Python. Note over here that you can also use CMake. However, we are going to use Amen Python, and then call the package simply as mobile robot. And if you now execute this command, you will see all the files over here. And if you list the content of the folder, you will see a new folder called Mobile Robot. Let's navigate to this folder and let's look into its structure. Namely, here you can see several files and folders. First of all, mobile_robot is the folder that can contain source files written in Python. Package.xml is the configuration file. Resource folder is the folder for resources. Setup.config and setup.py are configuration file, and then we have the test folder for tests. Here in this video tutorial we are going to create 3 additional folders. They are launch, model, and parameters. And if you again type this command, you will see that the launch folder is created, model folder, and parameters. The launch folder will contain the Python launch file that will be used to start all the nodes. Then the model folder will contain the model file, that is the files that describe our robot geometry and gazebo properties, and parameters folder will contain the YAML file that will define the bridge between ROS2 and Gazebo. Okay, so let's start modifying these folders and files. First of all, we need to create the URDF or Zacro file, then we need to create the Gazebo file, and then we need to create the parameter file. To do that, you need to navigate to the model folder. So let's go to the model folder, and inside of this folder you need to create a file called robot. To create the file, you can use your favorite editor. In my case, I'm going to use Visual Studio Code. If you want to learn how to install Visual Studio Code on a Linux Ubuntu machine, then you can watch a video tutorial I created. Simply go to my YouTube page and search Install Visual Studio Code on Linux Ubuntu. To start Visual Studio Code, I will type this, and the name of the file, as the manual suggests, should be robot.zacro. So let's create this file. If you go to Visual Studio Code, click on File, New File, and call the file as robot.zacro. Then save the file in the model folder, click on Create File, and over here, to save time, I'm simply going to copy and paste the content of the file. So here's the file, and I will save this file and I will explain the file line by line. That is, I will thoroughly go through every line and I will explain everything. Now, to do that, we need to bring up the robot geometry. First of all, let me do that. Here's the robot geometry. And over here are all the parameters of the robot. So I can do something like this and resize this terminal over here in this window such that we can see the robot geometry here and such that we can follow the file. Okay, perfect. This is good. Let me minimize and let's start. First of all, the purpose of this file is to define a robot geometry, to define some additional parameters, and to define the complete structure of the robot. Every URDF file or Unified Robot Description file format starts with this line. Then, this is how we write comments. So the comments are from the line 2 until the line 8. And over here we officially start with the robot description. We start this tag, robot, and note that at the end of the file you need to end the tag, and you end the tag like this. Let me close this window such that it doesn't confuse us. Good. So we learn to start a tag, we start with this and we end the tag. Then we need to specify the name of the robot, and this part is standard. Then we need to define geometry and constants. For that purpose, we are using the Zacro macros. That is, we can define variables at the beginning of the file, and later on we can use these variables in formulas. In this way, you can completely parameterize your robot geometry, and this really eases the modeling process. Namely, if you want to change some parameters such as dimension, for example, width of the robot, you will just go over here and change the value, and all the formulas inside of this file will be changed. So let's bring back everything over here. First of all, here we define the pi constant. Then we define the body dimensions. We define the ABC constants. So where are the ABC constants? So here's A, here's B, and here's C. That is there, the width, length, and the height of the robot body. Then we need to define wheel and caster dimensions. Namely, our robot has two active wheels. Here's the first wheel, here's the second wheel. Then you have the caster, here's the caster. These wheels are actively controlled. However, a caster is a passive spherical wheel that can only rotate. Then you need to specify the radius of the wheel, and you need to specify the D, the wheel width. Then you need to specify the constants S1, S2, S3, and S4. Let me now increase this so you can see these constants better. And let me zoom in to see what's happening. So here's S1, where is S2? S2 is here, S3 is here, and S4 is over here. They define the distances between certain centers. For example, S1 is the distance between C1 and C2. C1 is the point at the floor, and C2 is the center of our body of the robot. Now, the next step is to define mass and inertia. So first of all, we need to define the density. Here's how we define the density. Then we need to define the wheel material density. This is how we do it. Then we need to define the caster material density. I call these densities as D1, D2, and D3. Note over here that this is aluminum. Then we need to define the robot body mass, wheel mass, and caster mass. Namely, the robot consists of 3 parts, or 4 parts to be precise. We have the body, 2 links, and the caster. So we need to define the mass of the body. Here's how we define the mass of the body. Body is simple box. Then the mass is the density times the volume. The volume is A multiplying B multiplying C. We do the same thing for the wheel. The wheel is a cylinder. Again, you need to compute the volume of the cylinder. Here is the volume. Multiply this by density, and you will get the mass. And the same thing applies to caster. Here's the volume of the caster, and if you multiply the volume by density, we will obtain the volume of the mass of our caster. Then we need to define the moments of inertia. So here are the moments of inertia for the robot body. Since this is a body in 3-dimensional space, we have 3 moments of inertia. Actually, we have 6. However, since the robot is completely symmetric, then we have 3. To show you these formulas, I will go down, and that is I will scroll down this manual, and I will show you the formulas. So here are the formulas for the moments of inertia of the body. So here they are. Let me now do this and do this such that you can see them and you can see the implementation. Okay, so here they are, and this is how we implement them. You can see the implementation over here. Obviously, you can see that Ix is 1 over 12 multiplying mass multiplying B squared plus C squared, and you can see the formulas over here. We do the same thing for the wheel, where the wheel parameters, here they are. So we need to define Ix, which is actually called over here a little bit differently. It's called I wheel, since Ix and Iy are the same, and over here we define Iz also. Here they are, and you can see how these formulas are being implemented. And we do the same thing for caster. Here are the moments of inertia of the caster. Here are the formulas, and here is the implementation. Note that over here, these are the moments of inertia for a sphere. Then we need to define a macro that defines a complete inertial section of the robot body. Here is this macro. Here's how it's being defined. We start the inertia body, we start the inertial section, neglect this comment, then we specify the origin, we specify the mass, and we specify the inertia. We do the same for the wheel. We start the macro, we start the inertial section, we specify the origin, mass, and inertia. And we do the same thing for the caster. Here it is. The purpose of these macros is to simplify the implementation. Namely, later on in the code, we will simply type inertia wheel instead of typing something like this. This significantly simplifies the code. Okay, next we need to include additional files. Namely, in addition to this file, we will have to write another Gazebo file that implements the Gazebo parameters. And over here, we will include the file. To do that, we use this Zacro macro called include. We specify the path. Note how this path is elegantly defined. This find mobile robot will retrieve the absolute path to our model folder, that is to this folder over here, and it will return this path, and then the name of the file will be robot.gazebo. Note that we still didn't create this file. We will create this file after we explain this file. Next, we need to define links and joins. First of all, we need to define the fictitious link of the robot. This is necessary for Gazebo simulation. I call this link as a base footprint. Then I specify the joint name. That is, I specify this fictitious joint. It's called body link joint. Type is fixed. Then I need to specify the parent link, which is a base footprint, and the child is body link, which is defined in the SQL. So let's define the body link. For that purpose, let's bring back the file again, and let's look again into the geometry of our robot. So here it is. Let me expand this, and let's explain what's happening over here. Okay, so let's see. To define a link, you need to start a link tag and you need to end the link tag. But before we do that, let's just briefly comment upon and explain how things are being modeled in Gazebo. Note over here that the robot consists of 4 parts. These parts are actually links. We have the body link. This is the body, which is a box. Then we have wheel 1 link and wheel 2 link, and then we have a caster link. These links are connected by joints. Joints can be movable or fixed. In our case, we have 2 joints and the third one which is fixed. The 2 movable joints are wheel 1 joint, that is the joint that enables spinning of the first wheel. Then we have a joint that enables spinning of the second wheel, and then we have the fixed joint connecting the body and the caster. So let's define the body link. The body link obviously is a box size. We need to specify this is actually a box with this size, and we need to specify this in geometry section. And let's see what are the dimensions. The dimensions are A, B, and C, and this is how we specify dimensions. Then you need to define the displacements and orientation of the geometric center of the link with respect to the link frame. Here it is displaced for S1, that is, it's displaced for this distance. Then you need to define the collision section, namely to simulate a mobile robot in Gazebo, you need to define collision, such that collision can be detected. Here the collision section is simple copy of the body, or basically the visual section of the body, and over here we need to add the inertia macro, which is defined at the top over here. Okay, and you can see the elegance of using macros. You can simply specify something like this. This is especially useful if you have many different or a number of same, to be more precise, geometrical objects such as boxes. You can define this inertia and then you can just add this macro, and this simplifies the code. Then let's specify the back right wheel of the robot and the corresponding joint. So here it is. We need to specify wheel 1 and its link. So let's see how to do that. Simple. So you first need to define a joint. You call this joint as wheel 1 joint. The type is continuous. Continuous means that the joint can rotate for 360 degrees, and this can be done continuously. That is, the angle of rotation can take any value. Then you need to specify the parent link. The parent link is obviously the body link. The child link is wheel 1 link, which we will define in the SQL. Then you need to define here the origin. Then you need to define the axis of rotation, the axis of rotation is obviously the y-axis, that's why you have 0, 1, 0, and then you need to specify the max torque, here it is, and the max velocity in radians per second. And then you need to define dynamics properties such as damping and friction. Then we need to define link 1. Wheel link 1, we need to specify its origin. Note over here that you have rotation of the coordinate system for pi over 2. The rotation should be represented in radians, and these are the roll, pitch, and y rotations. That's why it's written RYP. These are the Euler angles, and you can see the translation over here. The geometry is obviously a cylinder, length is d, radius is r, and that's the visual section. Then here's the collision section, which is a simple copy of the visual section, and over here we add macro defining, or better to say a macro defined inertia, and that's the first link. And we do the same thing for the wheel 2 and its joint. So let's look at the wheel 2. First of all, over here we define its joint in the same manner as in the case of wheel 1 joint, and over here we define the wheel 2 link in the same manner, and that's it. Okay, the next step is to define the caster wheel. This is how we do it. First of all, we need to define the joint. The joint is fixed. You can see how the origin is rotated and displaced. Then the name is the caster link. Here is the visual representation. It's a sphere of the radius r. And here's the collision property, which is simply the copy of the visual property. And over here you add the macro defined inertia. And that's the end of the caster wheel. And here comes a very important part. To simulate the lidar, we need to define a lidar joint and a lidar link. Here I didn't represent the lidar, however the lidar sits at the top of our body. So here we need to define the lidar joint. The type is fixed. I'm displacing it for a certain distance over here. The parent link is the body link, the child link is the lidar link, and over here I need to specify the axis of my lidar joint, and the axis will be y. This means that my lidar will spin around the y-axis and everything will be in the horizontal plane. And then I need to define my lidar link. Again, it's a cylinder over here with a displacement. It sits at the top over here. Here's the collision section, and here's the fictitious inertial section, which I really don't care, since this is a small cylinder that spins with a certain angular velocity, and its motion doesn't affect the dynamics of the system. And that's the end of the lidar, and that's it. Okay, so let's save this file and let's continue further. The next step is to create the Gazebo file that defines the Gazebo parameters. Namely, if you go back at the top of the file, you will see that over here we have included the file called robot.gazebo. However, we didn't create that file. So let's create a file by clicking File, New File, and call it as robot.gazebo. And then make sure that you save it in the same folder. And to save time, here's the content of the file. Okay, so first of all, let's explain the purpose of this file. This file over here is the so-called URDF file. This file is used to simulate the robot in the RViz simulation environment. However, to simulate the robot motion in Gazebo, we need additional parameters which are specified by this file. Again, we start the file with the standard line. Here are the comments. Then we start the robot tag. At the end of the file, we end the robot tag. And let's see what's happening over here. First of all, for every link, we need to specify the mu1 and mu2 parameters. mu1 and mu2 parameters are friction coefficients. And we need to specify the material color. So you can see for the body link, you can see the parameters. Then you can see for the wheel 1 link these parameters, and you can see for the wheel 2 link as well as for the caster wheel. Note over here that for the caster I introduce a very tiny friction parameter, since I don't want my caster to obstruct the motion of my robot. Next, we need to define the controller for the differential drive robot. In our case, we are going to use the differential drive controller, and luckily the developers of Gazebo have implemented the differential drive controller plugin, and consequently we start this Gazebo tag, and inside of this Gazebo tag we need to specify the plugin file name. Then we need to specify the parameters. We need to specify what are the joints we are controlling, wheel 1 joint and wheel 2 joints. Then we need to specify kinematics, that is the displacement between the wheels. So if I bring back this thing over here, you can see that the displacement is 2 multiplying S4 and the wheel diameter is 2 times R, and that's precisely what's written over here. Here are the limits on the max acceleration, 10 meter squares per second. Then you can see, or 10 meters second square to be more precise. Here are the topics. This is very important. This is the command velocity topic. This is a TF topic. This is a odometry topic. This is a base. This is a child frame ID. This is very important to specify. And this is basically odometry publishing frequency. Note over here that we are not using the odometry since we don't want to track the actual position of the robot. We are using Lidar. And that's the end of the plugin. And then over here we also need the Gazebo plugin for the joint state publisher, such that we can transfer joint states. Here's how we define it. We specify the topic, then we specify the joint names, and that's it. And then here comes the part for the Lidar. Note over here that I have noticed that online there are a number of tutorials which incorrectly specify the Lidar, and consequently there are a number of errors and warnings in Gazebo simulation. This is the correct way for specifying the Lidar sensor. First of all, we need to specify the plugin name for sensors and the render engine. And then over here we need to specify Gazebo reference for our Lidar link. So let's explain this line by line. First of all, we need to specify the sensor name, then we need to specify the pose relative to. Here in our case this is a Lidar link over here. That is, we have defined the Lidar link in our file. Here it is, Lidar joint and Lidar link. Consequently, Lidar will give information relative to this link. We don't introduce extra pose. The topic that will be used to communicate this information is scan. The update rate is 1 Hz. We can improve this, for example, 2 Hz. That is, we will send scans 2 times per second. You can increase this. Here you can see additional information about the Lidar. You can see the scan properties, such as how many samples, what is the resolution, what is the min angle, and what is the max angle. Here we are covering 360 degrees, and this is the horizontal scan. You can also have a 3D Lidar, which will give you a 3D scan of everything. And over here you can see the range. The range is from, for example, 0.01 meters, that is from 1 centimeter to 12 meters. And you can see the resolution. Here, to make simulation more realistic, you can introduce noise. Here we are introducing very small noise and inaccuracies. This is very important for simulating real-life lidars. And we end the Lidar section, we specify always on, and we specify visualize 1. We end sensor, we end Gazebo, and we end robot. Let's save this file and let's continue further. The next step is to create a parameter.yml file that will bridge ROS2 and Gazebo topics. To do that, we need to create a new file. The name of the file should be bridge_parameters.yml. So let's copy this name. And then let's click on File, New File, and then here I'll paste this name. The name should be bridge_parameters, and make sure that you save this file in the parameters folder and create the file. Here again, to save time, I'm going to simply copy the content of this file. Oops, I didn't do it well. Let me copy and let me paste it now. Sometimes this paste command doesn't work properly. So sometimes I have to do this, then Control C, let's do it third time, and third time it will work. So what's the purpose of this file? The purpose of this file is to bridge Gazebo internal topics and ROS2 topics. For those of you who don't know what are the topics, ROS2 communication is based on topics. Topics can be seen as communication links. Namely, every ROS program will most likely send some information to another ROS program, and this is done through topics. Gazebo internally has its own topics and ROS2 has its own topic, and we need to bridge these topics. And here's how we do it. First of all, this is how we bridge the clock topic. This is the ROS type name, that is the type of message being transferred in ROS, and this is the Gazebo message name, that is the data type in Gazebo, and we specify the direction. Here we go from Gazebo to ROS. Then here is for the join state plugin, here are the topic names, then here's the ROS message type, here's the Gazebo type, and here's the direction. We do the same thing for differential drive plugin, that is for the odometry. Then we use for the TF, or the transformation topic, or coordinate system transformation topic. Then we do that for the command velocity. Command velocity is used to send control commands, and this is necessary for controlling the robot by using the keyboard keys. And finally, here is the Lidar. Here are very important things. The ROS topic name is scan, and if you go back to robot.gazebo and if you scroll down, you will see over here that the topic is scan, and this is precisely this topic over here. Here is the data type that's being sent, here's the Gazebo data type, and the direction from Gazebo to ROS should be specified, and lazy we set to false. And so let's save this and let's continue. The next step is to create the Python launch file. So let's learn how to do that. So let's create the file. The file name is given over here. So let's copy this file name. Let's click on File, New File. Then over here I'm going to paste this. Oops, I didn't make this. So let me do it again. New File. Then I'll paste Gazebo underscore model.launch.py. So let's save this file in the launch folder, and let's create a file. And over here, let's now copy the content of the file. So let's copy this, let's paste this, and here's the content of the file. Let's explain first of all the purpose of this file. However, the file should be saved in appropriate folder. Here I already did it, however it should be saved in the launch folder. Make sure that this is the case. Okay, so let's save this file and let's continue further. The purpose of this file is to start several nodes at the same time. Namely, we need to start ROS2 nodes and we need to start Gazebo simulation. So let's first of all import the necessary modules, libraries, and classes. This function will set up everything. First of all, we need to specify the robot Zacro name. Then we need to specify the package name. Then we need to specify the model relative path. This is the relative path of our robot.zacro file with respect to the path of the package folder. Then we need to specify several things. First of all, we need to retrieve the absolute path to the model, and this is how we do it. We use the OS path joint. Here we get the absolute path of our package, and then we specify the model relative path. Then over here we need to get the robot description from the Zacro file. We convert this to XML, and over here we need to specify the launch file from the Gazebo ROS package. That is, we need to retrieve the absolute path. Let me show you how it's being done. We are searching for the package name ROS_GZSim. We are searching for launch, that is, we are adding the launch folder, and the name of the file is Gazebo Sim Launch. So here's the complete line, here's the beginning, and here's the end. And this will retrieve the absolute path to this file. And note that this file is inside of the Gazebo package that we installed previously. That's why you're seeing something like this. Okay, so now we need to define the launch description. Here we are using include launch description, and let's see what do. We are specifying Gazebo ROS package launch, we are specifying the launch arguments, and over here we are specifying additional Gazebo arguments. They are the world, we are going to use an empty world, and we are specifying additional parameters. So let me show you the line once again. Here it is. This will simply specify and tell to Gazebo that we want empty world. That is, we don't want any kind of scene, just an empty flat surface, and that's it. And then we need to specify the Gazebo node, package name, executable create, additional arguments, and where is the output. We do the same thing for the robot state publisher node, robot state publisher, output screen, additional parameters. Here we pass the robot description, we're using the simulation time. Then we need to bridge the gap between ROS2 and Gazebo. We are specifying package, then we are specifying the parameters folder, and we are specifying the path, right? And this will retrieve the absolute path to the bridge parameters.yml file, and then over here is the node that established the communication between Gazebo and ROS2 topics. We pass our bridge parameter files as parameters, and we specify the output to be screen. Here we create an empty launch description object, we add Gazebo launch, and we add 3 nodes over here. So let me now correct this, and we return the launch description. And that's it. This is our launch file. Let's continue further. The next step is to modify 2 files. Namely, if I open the mobile robot folder, I will see setup.py and package.xml configuration files. So let's open these files, and let's start with the package.xml. Package.xml is a configuration file, and we need to specify over here the dependencies. Namely, our model has several dependencies. The model should depend on additional packages, and here they are. It depends on joint state publisher, robot state publisher, Zacro, ROS Gazebo, ROS Gazebo simulation, and ROS Gazebo bridge. So let's save this, and then let's modify the setup.py file. Here we need to do 2 things. First of all, we need to add these import lines. So let me copy this. Here we need to specify the beginning, and here comes a very, very important part. Namely, over here we need to specify several things. We have to make sure that our build system can recognize 3 additional folders we created. So let's be careful over here, and in this list let's add this. So first of all, let's add this line, and let's add these 2 additional lines. So what's happening over here? Here we are saying that there are files and folders located in launch, model, and parameters folder. This is very important since these are the 3 additional folders we manually created. That is, they are not contained in the original template. This is very, very important. Okay, so let's save this file, and let's say package.xml, let's say save Gazebo launch file, let's say bridge, this file and this file, and let's continue further. Okay, now we are almost ready to build everything. However, before we build everything, let's do additional modifications. First of all, let's open a new terminal. In this terminal, let's source our environment. Then let's navigate back to the base folder. In this base folder, let's install ROSDAP. ROSDAP is a tool that's used to verify that everything is installed properly. Then let's initialize. And then let's update ROSDAP. Okay. And then finally, let's run this command to verify that all the dependencies are properly installed. And as the output, you should see something like this. And finally, we can build our package by typing this thing. And let's hope that we will see no errors. So no errors. So far, so good. Now we are ready to run the created nodes and inspect the simulation. First of all, open a new terminal. And in this new terminal, source now the created setup.bash file. Okay. Here we are not sourcing setup.bash from the base ROS2 installation folder, we are sourcing setup.bash from the newly created package. And then let's finally run our simulation and let's hope that everything will be fine. Okay, here it is. Good. Now it's still a good idea to go back and to analyze, are there some warnings or some errors over here? Currently, I don't see any specific errors, maybe few warnings. However, here's our simulation. Here it is. Beautiful. Looks beautiful. Next, let's explain how to visualize our Lidar. So click over here and search for Lidar or visualize Lidar. Click here and you will see the menu here. Let me now change this and show you the menu. The menu is here. Now click on this button and after you click you will see that this scan topic is detected and you'll see all the rays. They look beautiful. You can see the range, you can see the point size. Now, what I suggest over here is to play with these options. If you click over here, only the rays that are being reflected from a surface are being shown. Since there is nothing to reflect from, there will be no rays. Okay, so let's add surfaces and objects. So click here and place the box over here. To verify Gazebo installation, or better to say to verify Gazebo simulation of Lidar, let's approximately try to put this box at 3 meters. So let's see, 1, 2, okay, 3 here. Okay, so here it is. Okay, here it is. And now you can see magic happens. So if you see now, there are only non-hitting rays, right? And then you can add some other surfaces. So you can add a box, you can add sphere, you can add something like this over here, or you can add another one and you can add an additional one over here. Okay, so this is very good and promising. Good. Let me now finish with this one and that's it. Good. Next, let's learn how to inspect, is our Lidar working correctly. If I now open a new terminal, in this terminal I need to source the environment once again. So let me do that. Here I need to source the base environment. And let's look into the topic by typing ROS topic list. And over here you will see the scan topic. This topic is used to transmit the Lidar measurements. So to obtain information about this topic, we need to type ROS topic info and then the name of the topic, scan, and you will see the type of messages being sent. So let's inspect this message. To do that, we need to type something like this, and here you see what type of messages are being sent, and you can see the message content, you can see the field. It contains the header, frame ID, angle min, angle max, angle increment, time increment, scan time, range min, range max, and ranges. For us, the most important thing is this field, ranges. This field will give us the actual measurements. So let's in real time investigate the measurements. To do that, you simply need to type this command. That is, you need to echo the information transferred through the scan topic, and the field should be ranges. And if you press enter, you'll see what's happening. Every second we have 2 messages, and if I press Ctrl C to kill this, you'll see what the message is. Namely, you will see the array and you will see what's happening over here. Okay, so let's explain what are these values. Infinite means that the ray corresponding to this position is not being reflected, right? So this is very, very important. Then we have something here, 3 point something, which is most likely, if I now bring back this box, since this box is placed at 1, 2, 3 meters. So this is the measurements of the box, and this means that your lidar is working properly. Good. Next, let's keep this command active and let's open a new terminal. And in this terminal, we will start the teleop node. The teleop node will enable us to control our simulation. Let me now rearrange everything here. So let me do this, let me do this. Here it is. Let's open a new terminal, and inside of this new terminal, let's again source the environment. And then after sourcing the environment, let's run our teleop node by typing this. Okay, and now I can control my simulation by using the keyboard keys. Let me now just change the size over here. Here it is. Okay, to change or to modify the robot position, you need to use these keyboard keys. So let's start doing this. So if I press U, I will have rotation. If I press I will move forward. L is the opposite. M is back, etc. So you can obtain this type of motion over here. And of course there's collision, everything is being detected. Okay, now to increase the speed, you can simply press Q to increase everything, and you can see how nicely the collision is being done. You can see that this box is being moved, which is really, really amazing. Okay. And now let's see what's happening. If you now bring back this topic, you will see how the motion is detected and how the obstacles positions are changing. This means that our lidar is working perfectly. Okay, that's all for today, and thanks for watching.